AI coding assistants have massively accelerated the modern software development lifecycle. By automating syntax generation, engineering teams push applications to production at a velocity that was physically impossible just a few years ago. This rapid acceleration introduces a severe paradox. The faster these models generate output, the faster they introduce structural weaknesses into the application layer. This data visualization charts the output reliability of leading AI coding assistants. As of March 2026, research indicates that between 48% and 62% of AI-generated code snippets contain high-severity vulnerabilities or design flaws right out of the prompt. Those high-severity defects group into three specific categories: direct code vulnerabilities, unmanaged data exposure, and strict legal or compliance violations. These models bypass traditional defect patterns by injecting entirely new categories of systemic risk directly into the enterprise architecture. To safely integrate these tools, engineering teams must map an updated threat model for the AI-assisted pipeline and deploy specific mitigations to intercept those flaws before compilation. Applying development speed to an unverified output stream is simply automating liability. This diagram outlines a traditional pre-AI software pipeline, moving linearly from developer environment to deployment. When an LLM assistant is integrated, it docks into the local environment, injecting rapid, automated pulses of data downstream into the codebase. These models generate syntax by matching patterns across massive datasets, frequently reproducing outdated and insecure coding practices verbatim. This deterministic pattern matching routinely suggests unparameterized SQL queries, a direct path to SQL injection attacks, and regularly embeds hard-coded API keys and credentials directly into source files. When developers spot these errors, they often rely on the iteration fallacy, the assumption that feeding the error back into the prompt will cause the AI to refine and fix the initial bugs. This line graph measures prompt iterations against critical vulnerabilities. Empirical data shows that after 5 revision cycles, the resulting code contains 37% more critical vulnerabilities than the original output. Repeated revisions flood the model's context window, the total amount of text the AI can process at once. As it fills with conflicting corrections, the model loses track of the overarching application architecture, and the logic actively degrades. Beyond internal logic errors, generation introduces specific external supply chain vectors. The most prevalent is package hallucination, a scenario where the AI confidently suggests importing entirely fictitious, non-existent software libraries to solve a problem. Threat actors actively monitor common LLM outputs to identify these fabricated libraries. They then create malicious packages using those exact hallucinated names and publish them to public registries. Developers unquestioningly run the AI-suggested install commands, downloading the malicious package and granting the attacker direct access to the deployment environment. Relying on an LLM to iteratively debug its output does not refine the logic. It actively compounds structural rot within the application stack. Looking past the internal codebase, we find a wide two-way data tunnel connecting the local environment directly to massive third-party LLM vendors. This unmonitored connection creates a shadow AI environment, software and data flows operating entirely outside of managed IT controls. The primary outbound risk occurs when developers paste confidential proprietary logic or internal code into the assistant for debugging purposes. That proprietary data is permanently absorbed into the vendor's training set, potentially surfacing verbatim in autocomplete suggestions for competitors. The connection also introduces the inbound risk of prompt injection from external threat actors. Attackers can feed crafted inputs into the model to manipulate its behavior, forcing the AI to bypass its own safety guardrails, reveal hidden system instructions, and exfiltrate sensitive local information. These data exposure risks multiply during deployment, particularly with the rise of vibe coding, a practice where non-technical users generate entire applications purely through conversational prompts. Because these users lack security expertise, the auto-generated applications frequently compile with overly broad data permissions. The result is raw internal databases accidentally deployed directly to the public internet, completely lacking standard authentication layers. Unmonitored AI coding assistants dissolve the traditional enterprise perimeter. They transform secure local environments into massive, unmanaged data siphons. Technical vulnerabilities are only half the threat model. AI-generated codebases also embed invisible legal risks. The most immediate is IP contamination. IP contamination occurs because LLMs frequently regurgitate large, verbatim chunks of licensed or copyrighted code directly from their training data without providing attribution. Utilizing this unattributed code in a commercial product directly violates licensing agreements and invites severe intellectual property litigation. Beyond intellectual property law, LLM architectures suffer from strict regulatory blindness. AI assistants possess zero contextual awareness of sector-specific compliance frameworks like GDPR, HIPAA, or the EU AI Act, which becomes fully enforceable in August 2026. This blindness routinely causes the AI to architect non-compliant data handling structures that invite catastrophic regulatory fines. These overlapping violations create an overarching legal black box of liability. When AI-driven harm occurs, there is current legal ambiguity regarding who bears actual responsibility: the tool vendor who trained the model, the individual developer who prompted it, or the deploying enterprise. Treating raw AI output as production-ready upgrades, standard engineering bugs into direct, unquantifiable legal liabilities. This is the fully compromised pipeline we have mapped. It illustrates the overlapping vulnerability paths, shadow AI leaks, and compliance failures inherent in AI generation. Securing this pipeline requires a total abandonment of implicit trust in LLM outputs. Safe AI integration requires implementing continuous exposure management, or CEM, as a strict architectural framework. The first mandatory pipeline patch is the human-in-the-loop review. Security teams must mandate that experienced developers review all AI-generated logic. Every line of suggested syntax must be treated strictly as untrusted external input. The second patch is shift-left automation via SAST and SCA tools. SAST stands for Static Application Security Testing, and SCA stands for Software Composition Analysis. By integrating these automated tools directly into the generation pipeline, they actively intercept hallucinated packages and detect hard-coded secrets in real time, well before the code ever reaches compilation. The final, macro-level patch requires establishing strict AI governance policies. Enterprises must enforce an acceptable use policy that explicitly defines sanitized data sharing boundaries and restricts internal usage to sanctioned enterprise-grade AI tools. This patched architecture allows an organization to harness the acceleration of AI generation while actively neutralizing its inherent chaotic outputs. AI models are incredibly powerful syntax generators, but the mandate for security, compliance, and architectural integrity remains a strictly human responsibility.